All right. So what we're going to do today is we're going to talk about circuits, okay? And we're talking about electricity. And in the last part of Unit 1, in 1.1, we talked about the transfer of power through mechanical means via simple machines or by gears, sprockets, belt and pulleys, those types of things. What we're going to do today is talk about circuits. And there's a couple of things that we need to know. So in your notebook, I would make me a little T chart like this. And we're going to start out, we're going to talk about two specific types of circuits. We're going to talk about series and parallel. Okay. And also, one of the kind of the fundamental things that we're going to talk about as we go through this is this idea of Ohm's Law. Okay. And Ohm's Law, and I like to do it in a triangle. If you know what I'm doing with the triangle, we're going to have voltage, current, and resistance. All right. So a couple of things that we're gonna know about series, and we're gonna start with a series circuit and kind of talk through it. Is that there's only one path for the electricity to flow. Okay, only one path. Hey Mason, can you shut that door for us? And so also, um, we're going to talk about then in, I like to change colors. So in a parallel, if there's one path in a series, what do you think about parallel? Well, two or more paths, right? And you may have already known that. Hopefully you did. Okay, so we're going to kind of put this aside for just a second, and I'm going to talk specifically about these things: voltage, current, and resistance inside of a series circuit to start out with, and then we're going to talk about it inside of a parallel circuit as well. Okay, so let me switch over here. One of the things when I'm talking about voltage, okay, remember it's going to be volt, and then and it's also its SI unit is volt, and its variable is voltage. So an example of that, I might say 12 volts. Okay, going back to this, all of these, like that one's going to be in voltage. Current is measured in amps, and resistance is measured in ohms. And I'll write the little SI abbreviation kind of down in the corner because they're different than the variable we use in the equation. Why? I don't know. I don't have a good answer. Um, I just don't know. Okay. Oh, that's better. I can put my face on the screen. Okay. So we're going to go back to this idea of voltage, and I've given you the example. Now, voltage, the thing that I remember about voltage is there's two ways that I kind of think about it. The first way is that it's the force. Okay, it's the electrical force. It's the push. We're going to talk a lot about water, and we're going to use water to kind of explain electricity because it's really analogous. And so if I think about water going through a garden hose, right? If I think about water going through a garden hose, and if I just had water just barely coming out the end, right? Thank you, Jordan. If I just barely had water coming out the end, okay, and then I wouldn't have a lot of force, but maybe the hose was full, right? So like the hose is full, the water's running out the hose, but it doesn't have a lot of force. Think about it like a fire hydrant, like the fireman's hose, right? If you hook one of those up, all the water's coming out and it's blasting out the end, right? So that water, we've got an amount, and then how hard it's pushing is the force. So that's a lot the same with voltage. The other way that I think about voltage that makes it a little bit different is voltage is also the potential energy difference on a battery. So if I look at a battery, let me get one out here. Here's a battery, right? It has a positive and a negative side, okay? The voltage is the potential energy difference between these two sides, okay? And in a AA battery like this, it's 1.5 volts. So is a AAA, a C, and a D. They're all 1.5 volts. And so I think about potential energy and I think about the height, right? So if I had, and this is where my really fantastic art skills come in. This is going to be a dam, and behind that dam is going to be a lake. And then down here is a river, right? You guys understand how dams work, right? And so all this water behind here has a potential energy, right? And so it has, if it was unfeathered and let run, it could bust out and it would have all of that force with it, and it would be going pretty fast if you've ever seen a dam break. So that's kind of like voltage. Well, what's stopping it here, and we'll talk about this a little bit later, is this resistance, right? This dam is resisting the water. Okay. So we're going to talk about, so almost like on this guy here, that let's say that this is the positive side of, and this is the negative side, much like that battery. So I have that, I could measure that same thing here. If I measured this height difference between, and I said, what's the height difference between here and here, right? I could say that's my voltage. That's that potential energy difference between those two things. And I kind of like to think about it like that. So we could measure this in a circuit. We can know this, and in a series circuit specifically, one of the things that we're going to talk about here in a little bit is how does the voltage and resistance, how do those things add up? So if I looked at this circuit, so hang tight on this. So I'm going to put this aside. I'm going to draw the same exact thing. And let's just, for easy math, let's say that the value of this dam is, we're going to say 1200 ohms. Okay. So remember that our resistance total here is 1200 ohms. All right. I'm going to put that over there. I'm going to redraw this exact same thing. And I'm going to draw it a little bit different. I'm going to draw it in 3 parts. Okay. I'm going to draw one dam, and this one's going to be a little bit higher, and then the third one's going to be a little bit bigger. So let's say this one's 300 ohms, this one's 400 ohms, and this one's 500 ohms. Okay. So I still have the lake that flows out into a river, that flows out and flows out. Okay. So if I think about this, now I have 3 resistors. Let me slide that up, doing the job of what this one was doing before. This height difference is going to be the same here. So the potential energy, we're just doing it in stages now. So the difference between this surface and here is essentially the same. Okay. Is essentially the same between these guys. And let me just draw out the circuit that if I was going to draw this schematically, if I had a battery and I have a resistor, and I have another resistor. So this one would be 300, this one would be 400, and this would be 500. Okay. So going back to our chart over here, one of the things that we can know about our resistance in a series is our resistance total is a sum, SUM, of the parts. Okay. So basically what we did here is we said 300 plus 400 plus 500 is equal to 1200. Those things are the same. Okay. I just broke it up into little bitty pieces here with little bitty dams. Okay. So that's the rule there on in a series. Now this is only for a series, and so that's how the resistance works and the voltage. And so what happens if I was going to measure the potential energy difference of the whole circuit, it's this, the total height. But now if you think about it, I've got the height here, right? I've got the height here, and I've got this third height here. Well, if I add all three of those up, it equals the total height, right? So this would be the voltage at resistor 1, the voltage at resistor 2 difference, and this would be the voltage at resistor 3. All of those equal my voltage total. And they even call this, they have a word they say voltage drop. So when I look at these components, if I measure across these components, this is a positive side, this is a negative side, say, of this resistor. If I measured across that, I would have a potential energy difference across this resistor, positive side, negative side of this resistor, positive side, and across those resistors. So when I go back to that sheet where I look here and I say my voltage total, once again, is also a sum of the parts. Okay. So I know those two things about a series circuit. Okay. Now we're going to talk about current. Okay. And we've got mount electricity. And off of mount electricity, we got to have a sun here. Can you see my sun? Sun shining nice today. I should have been an art major. We have a river that flows, okay? And it flows out into the ocean or the sea, we'll call it. Okay. And what happens with this current is we use water a lot. Now, there's a couple things we need to know about this particular river. Is notice that there's just one path, right? We just have one path. There are no tributaries feeding this river. Okay, so it's almost like it's in an enclosed pipe. Okay, so the amount of water that flows in here on the mountain is the same as what flows out. So our input is equal to our output in a series circuit when we talk about current. Okay, let me have a drink. A coconut smile. So I do a lot of kayaking, and we measure the flow of water at cubic feet per second. So like how many cubic, like little boxes, like a foot by foot by foot box flow by a certain place at a given amount of time. So if I came up here and I just tapped into my pipe and I measured it and it was 100 cubic feet per second here, if I came down here and I measured it, it would once again be 100 cubic feet per second. Okay. So this is in a series circuit. So if we go back here to our series circuit, our current, okay, current total is, our current is always the same because there's only one path. And so the same thing, if you think about that garden hose, if you go to the wall and you turn it on just a little bit, where maybe just a couple of drops are coming out the end of the garden hose, how many drops are going in at the wall? The same amount, right? No matter what the resistance is, if it's wide open, the same amount of water going in that hose is the same amount of water going out. So in a series circuit, going back to this guy here, it's the same thing. It's one path. So what's coming in has got to be going out. Okay. So now let's say that I put a mountain range right here and I blocked the flow of my river. Okay. Okay. And so what has to happen now is the river is going to take, part of it's going to go behind the mountain and part of it's going to come back in front of the mountain and it's going to rejoin down here. Okay. So when I'm talking about just this section right here, how many paths do I have for the water to flow in? 2, right? So I've created a parallel path. So I have 2 or more paths. Okay. So now if I looked at this and I said, okay, I'm going to measure, I'm going to tap into this closed pipe and I'm going to measure here and I'm going to say that it's 60 CFS here. Okay. How much has to be flowing through the other branch? Remember, I had 100 going in and 100 coming out. What has to be flowing through this side? 40. Very good. Okay. So going back to my sheet here, over on the parallel side, I can say that current is added from each branch to get total. Okay. So current, and an example of current, let's say I was going to write something, might be like, we might have something like 0.002 amps, which would be 2 milliamps. Okay. I wanted to write that, and its symbol is I. All right. So that's current. Okay. And so we've kind of going back to this guy now. Let's talk about a parallel circuit. And I'm going to have 3 resistors. I got my bateria. And I like doing this in multiple colors. Because if I have a parallel circuit and I've got 3 paths and 3 resistors on this guy, and we could use those exact same values as we used before. We could say 300, or we say 400 and 500 ohms, right? That's the Greek symbol omega, and we'll say 12 volts again. Okay, so notice this. Think about going back to the water hose. If I had water flowing out here, it's going to divert into 3 different pathways, right? Well, going back to that, if you thought about this as 500 is a bigger resistor, right? Well, the more I resist, the less flow I'm going to get, right? Okay. So we should think about that in terms, if I just looked at that and I said, which one of these branches is going to have the most amount of current flowing through it? Well, it's going to be the one with the least amount of resistance, right? So you can look there and you can say, well, this one right here is going to be that one. Okay. Is going to be that one. So what we're going to see here is, so we said current is added, but what I think about with voltage is, remember, going back to that dam, is that I have a positive side and a negative side to my circuit. And in a series circuit, when we drew that series circuit, each one of these components, right? There's a positive side, and a positive side to each one. I'm gonna get it upside down. There's a positive and a negative side to each one of those components. So I have a potential energy difference across each resistor. Okay. So just like I have these 3 voltages, when I look at this parallel side, I've got a positive side of this parallel circuit, and then I have a negative side to this parallel circuit. So the height, the potential energy difference is the same across the circuit. So if I'm measuring positive and negative, and I put a meter here and a meter here, because look at all this wire is all connected. I could measure it here like that. I could measure it there. Still going to get the same reading. I could measure it there, 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 there. It doesn't matter. It's like 2 sides of a coin. It's like a heads and a tails, a positive and a negative. Okay. So what we know about voltage in a parallel is that our voltage total is always the same. Okay. So it doesn't matter in here what happens. Okay. Just two sides to that circuit. Now, the last thing we're going to talk about is resistance in a parallel, okay? A resistance in a parallel. Now, remember, in a series circuit, it's a sum of the parts. So we were able to add up these three resistors and we got the 1200 total, right? Because these three dams are equivalently the same as one big dam. It doesn't matter. In a parallel system, it does not work like that. In a parallel system, and this is what I always tell people, is you're just going to remember, we're going to remember this as the odd formula, okay? We're going to remember this as the odd formula. And what it says is that our resistance total in parallel is equal to the reciprocal of the summation of the reciprocals. And this is the formula. Project Lead the Way gives us this formula, and I'm going to write both of them down. And they also give us this formula, and both of these equals, 1 over R1 plus 1 over R2 plus 1 over R3. Okay, so these two formulas it gives us, and I'm going to tell you something right now. I don't like either one of these formulas. I have kids that every year, I like it just conceptually. Maybe you can understand what's going on there, but I have kids that, and I want you to write this down in your notebook, highlight it, underline it with your glitter pen, whatever you got to do, and it's this: when in doubt, parenthesis it out. Go ahead and write that down. When in doubt, parenthesis it out, because most of the errors that I get from my students are just simply we didn't put it into our calculator correctly. And I know this, that the more parentheses that I use, the more likely I am to get. It's like it's a, we were talking about, there's a proportionality there for me. So like if I was doing this formula right here for this particular problem, I would put it in my calculator like this. And I know this is overkill, but I'm going to go parentheses 1 parentheses. Okay. And I'm going to go divided by, and I'm going to go parentheses, and then I'm going to open up my parentheses again, and I'm going to say 1 divided by, well, R1 in this case is going to be 300, parentheses, plus, open parentheses, 1. Then I'm going to go 400, plus, parentheses, 1 divided by 500. I'm going to close that, and then I'm going to close that, and I'm going to hit equal. Okay? So that's this formula all laid out. That's a lot of typing, right? That's a lot of places to make a mistake. But if you do it like that, you're going to get the right answer every time. I promise you. Okay? Now, here's the rule about this that I want you to kind of make a note about this too. So besides the when in doubt, parenthesis it out. Remember, parentheses are like little math hugs. They make you feel good. Okay. Now, here's the rule. RT in a parallel is always going to be equal, or it's always going to be less than the least. Okay. There's your cheat rule. Does it make sense? If you're checking that at home and you're saying, does it make sense? Your resistance total in parallel is always going to be less than the least. So if I'm just looking at a multiple choice test and my answers are A is 127, B is 304, C is 500, and D is 1200. There's only one of those answers that's less than 300. It's got to be that one. Okay. It's got to be that one. So that's my rule on that. Now, here's the way that I'm going to teach you to put that in your calculator. You ready? Here's the formula for resistance total and parallel. We're just going to use inverse. So if I was putting that in my calculator, I would say 300 minus, and now I want you to go ahead and do this so I know that you can do it, and then tell me what you get. That's why you got your calculators. Don't forget the last inverse. That's going to give us our resistance total. So when you get it, tell me if you got a number that makes sense. Did you get something less than the least that's not a decimal? If you got a decimal, you probably didn't put this. If you get like 0.00 something, you probably didn't do this last -1 outside of the parentheses. That's why you need a calculator and probably not your phone too. Patrick, did you get it? What'd you get? Ding, 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 ding. Hey, what did I say back here? That's a pretty good guess, wasn't it? So there's what I got. 127.6595,745. There it is. So, all right. So make sure you can put that in your calculator correctly. That's going to be a big help to you when we're doing these, okay? All right, so now we're going to go over those formulas real quick. So same kind of a different T-chart, but we're going to do our series and our parallel formulas. Voltage total. The voltage at resistor 1 plus the voltage at resistor 2 plus the voltage at resistor 3, however many we got. Our current total is current at resistor 1 plus current at resistor 2 plus current at resistor 3. Remember, they're additive. Our resistance, no current, that's not right. Not plus. Sorry. Got ahead of myself. Let's go equals. Resistance total is the summative, R1 plus R2 plus R3. Okay. So then on the other side, we have our voltage total is all of these are the same. So our voltage at resistor 1 is equal to our voltage at resistor 2, which is equal to our voltage at resistor 3. Our current is additive here. The different branches, remember, add up. So our current at resistor 1 plus our current at resistor 2 plus our current at resistor 3, however many we got. Okay. And then this is the funny one. Our resistance total is R1 inverse plus R2 inverse plus R3 inverse of all that. And then don't forget your Ohm's Law. And I'll write it down here. And you'll need to know here that this one, you might make a note on here, is Kirchhoff's voltage law. And this one is Kirchhoff's current law, KCL.